Yep. Okay. So we can wind down from quite a technical talk by Niklas, and this is going to be slightly more simple. In fact, maybe this is a runner-up for the simplest paper that we've seen in this conference. You let me know at the end. So what we're going to talk today about is about who gets to enjoy the informational surplus in Bayesian persuasion, and I'll quickly go over the motivation because this is very, very standard. You want to think about, say, a policymaker who turns to some experts for advice on the potential impact of a policy. Typically, such an expert might have different incentives for the policymaker. And then there's an example here, which will pop up later in the talk, is you want to think of maybe the policymaker cares about the impact of the policy on society as a whole, while the experts, although they do care about society as a whole, but maybe they're somewhat inclined to care about a particular sector within the population. And the expert is going to be knowledgeable, of course, and the policymaker is going to take the action. And now we know that from the famous papers of Hahn and Maschler, and more recently, I mean, 10 years ago, we discovered by Kamenik and Gensko, we know how the experts can enjoy the informational surplus that exists. And in this, in the standard model, the policymaker turns to this single expert that is out there, so he doesn't get to choose the expert. There's only one expert out there, and that is the result. And the question we ask here, what if the policymaker can choose the expert he turns to because there are a few experts out there? What happens then? Who gets to enjoy the informational surplus? I'm going to go similar to Piotr mainly through one long, simple example to demonstrate what's going on here. This will lead to our main result in that example. And from that, we will have maybe two surprising corollaries, two surprising observations. And then, time permitting, I will actually give you the more general model and frame and give you the actual general result. And at the end, I will discuss briefly related literature. So here we go with the example. As I already mentioned, we're going to think about the receiver as a policymaker, and he has to choose between two actions, whether he adopts a given policy, and we'll refer to that action as P, or he rejects it and maintains the status quo, and we'll use Q for the alternative action. Now, in terms of the hidden states, what is unknown, the policy either improves public health, so recall this is a policy regarding e-cigarettes in the example. So it is either the case that adopting the policy will improve the public health or will not improve the public health, and the two states are going to be denoted H and H bar. And the policymaker wants to implement P only when it improves the public health. In addition, it is unknown whether the policy causes a decrease or an increase in tobacco use among youth. We'll denote, if the policy increases tobacco use among youth, we'll denote that state by Y. And so it decreases, it's going to be Y. And an increase is going to be Y bar. And answers the expert. Yes, sir.
Sorry, Rann, I'm sorry, just to clarify, so that means that either P is better than Q or worse than Q. That's what you mean by the H and H bar? Is that? I didn't parse that sentence well, so I want to understand.
So for H and H bar, either the introduction of P improves the public health,
either P is better than Q or worse than Q for the policymaker. That's what you mean.
Yes, if P does not improve public health, then the policymaker wants Q.
Okay.
And the expert has a similar view of life. The expert is similar to the policymaker. If the public health is improved by the policy, then the expert also wants to adopt. But in addition, he cares about youth. So if it decreases tobacco use among youth, then he's also he prefers the policy over the status quo. Okay, so this is the story we have here. And to put this in a more formal setting, so we use math to make things much clearer. So the state space is going to be the product of the possibility, the impact on the policy's impact on the general public and that on youth. Recall H is always the desired state, and non-bar is the desired state and bar is the undesired state. The policymaker would like to adopt P in states HY and HY bar. He doesn't care about the youth, he only cares about the general population. On the other hand, the expert wants P adopted in 3 states, HY, HY bar, but also if the public health is not improved, but the youth consumption of tobacco decreases, so H bar 1. And again, to make things simple, whenever you get your desired outcome, you get a 1. And when it's the undesired outcome, you get a 0. And we're going to think of the prior distribution over the state space. The probability of H is going to be something greater or equal than 0.5, denoted by alpha. And the probability of the impact on youth, the decrease, is going to be beta. Any number between 0 and 1 will do. And these things are independent in our example. So it doesn't take too much to be convinced that the expert's optimal policy is always to recommend an action that is optimal to him. Right? So why? When he does that, note that the policymaker always adopts the recommendation. Okay? Because alpha is greater or equal than 1/2. And obviously that's optimal for the expert because he always gets what he wants. Okay. So in particular, this means that the expert always says P unless the state is H bar, Y bar, in which case he recommends Q. This obviously means that this is an expert optimal example. So this is completely optimal. He completely enjoys the information that he has. And it is not optimal for the policymaker. The policymaker enjoys some of the information, but definitely not the whole thing. Now, let's assume there are 2 experts out there. And we're going to think about these experts as almost as twins. So we're going to have a replica of E1 of our original expert with a slight change. They're going to be almost twins. So the 2 experts are going to be E1 and E2. And as before, E1 is our original expert. He cares about tobacco use by youth in addition to the public health. Right? He cares about public health, but he also cares about the youth. E2 is very similar, although he doesn't care about youth, he cares about women. So the state space for this example is going to be the Cartesian product of H, Y, and W. Again, W is the good thing that for E2. E1 is going to would like the policy to be adopted either if H or Y are realized. In other words, it is in every state except the 2 states that I mentioned here in the bullet, H bar, Y bar. And whether W or W bar happens, he doesn't care. And E2, his twin, is the same thing, but except he doesn't care about Y or Y bar, he cares about W. So he's going to prefer P in all the 8 states, in 6 states, namely all of the states except for the 2 that I write here. And similar to the original example, 1 and 0 are going to be the payoffs. And very similar to the original example, we're going to denote by alpha the probability that H is the outcome when P is preferred, when P is adopted. And Y and W both happen with probability beta and are independent. Now, we're going to assume in the sequel that the expert's signal can only depend on their payoff relevant state. So E1 can only signal information about H and Y, and E2 can only signal information about H and W. And I will say something about this when I get to the general model. So under these assumptions, what happens if the policymaker now chooses one of these experts? So he faces the same problem. He will face one expert which is very similar to the expert he faced in the original, but now he gets to choose which of the 2 experts. So the experts compete among themselves in the design of the information of the signaling scheme. So what I want you to have in mind is the following game played between two information designers, the two experts. Both experts initially propose a signaling scheme. The policymaker then chooses one of the experts. A state is realized and the policymaker chooses the action based on the chosen expert signal. Okay, so the restriction here is the policy gets to choose one expert to listen to. And you could ask at this point, why restrict the policymaker to a single expert? Maybe that would be a critique of the model. So let me right off the bat say something about that. First, from a descriptive point of view, I don't know how many of you tried to get involved in your respective countries about policies related to COVID-19 when the pandemic started breaking out. I for one tried to see how I can get a hold of decision makers and make an impact and maybe contribute something. I think that as a game theorist, I think different than epidemiologists, different than doctors and so on. So I thought I might add, as an expert, something, I might have something to say. It was impossible to get the attention of the decision makers, just completely impossible. So decision makers just don't have time, don't have the bandwidth, don't have the attention span to talk to all experts. So that's a descriptive reason why our decision maker chooses a single expert, because he doesn't have the resources to listen to all the experts. And another motivation for restricting attention to is a normative motivation, and this follows from the theorem. And the theorem is that in the game I just proposed, in every mixed equilibrium, the policymaker always takes the correct action. So experts have no choice but to contribute all the information that is payoff relevant to the policymaker. So the policymaker will reap all the informational surplus. The experts will reap whatever is left over. So whatever they can get under the result that the policymaker gets to enjoy it all. So that's also the answer to the question, a normative answer to the question, why look at a single expert? Because that is the right thing for the policymaker. He cannot do any better, obviously. Now, if we look at the numbers here, in particular, the policymaker gets a utility of 1, so he always gets his preferred action. And the expert utility, you might want to remember this formula or revisit this formula later on, gets something which is slightly beyond the guess, which is alpha, plus 1 minus alpha, 1 minus beta. I mean, you don't have to try and figure out where this calculation comes from. These are very simple. Now, let me give you some intuition about this result is true. I'm surprised that Sergio did not ask anything so far, but Sergio, listen carefully. I'll tell you, here's an answer to your coming question. So why is this information? I tried my best, go ahead.
No, so suppose that in fact there is just one expert who hears, I mean, your assumption that you are not allowed to use Y if you are the second one, or not allowed to use W if you are the first one. Suppose I'm just one expert and I can commit. I can really generate my the two clauses you are talking by committing not to use something that I know, because I know both Y and W. Okay, then do you get the same result, or is there still something that I'm missing?
I get the same result. In fact, all that is needed is that you cannot fully disclose the other piece of information. So you might be an expert on children because children are very important to you. You might know something about women, but you're not as qualified as an expert as the other expert who cares about women.
But that says,
or alternatively, you can commit to not fully using that information.
But still something that doesn't work right, because again, I'm an expert and he says, look, I'm going to propose to the policymaker 2 plans, yes, and let him choose whatever he wants. And everything is, and in each one of them, I'm committed to ignore something that I know, and he's going to choose one of them. And at the end of the day, everything is perfect. So something here is not right. Something I'm missing.
So I'm not sure I follow. You're thinking about a scenario with a single expert?
Yes. And
The
he
single
plays
expert.
the role of both of them.
Sorry?
That's what I'm saying.
No,
Yes.
no, but when he plays the role of here, the competition between them is going to be important. So let me give you the intuition for the proof, and I think that would partly answer your question.
Oh, I see. It's
and
the
would also say that I was correct in anticipating your question.
Okay. The payoff of the expert, I see. Okay. The answer to my question, I know what it is now. It's the payoff to the expert depends on what he knows and cares about, and not about the other thing. So if I take an expert that's going to imitate both, if he cares about both things, then he gets a different payoff. That's the answer. Okay, I figured it out. Thanks. Sorry.
Okay, so a bit of intuition about why this result holds, and this is essentially extends to the more general model that I will maybe get to in a minute, is, well, suppose this is not the case. And suppose, for example, expert one is chosen, say, with positive probability or with probability 1, and expert 1 does not fully disclose the information that is relevant to the receiver. Okay, he does not fully disclose it. Well, if you look at how the example is structured, clearly when the state is H, so when it is preferable for both to adopt the policy because of the public sector, then obviously E1 will recommend to adopt, because this is better for him, right? They're fully aligned. So it can only be the case that E1 recommends to adopt with positive probability when the state H bar holds. That is the only case that is possible under the assumption that the receiver does not get the full information. Okay, so there's some positive probability that he recommends P while H bar is the correct state of the world. Whatever Y is, and particularly he will do it when Y is the state and not Y bar, obviously. Now let's think about E2. From E2's perspective, he says, well, assume E1 is chosen. That induces a distribution over the preferred action P and Q. What I can do is, first of all, when I can commit when H is when the state is H, I will also say P. But what happens when the state is not H? Well, let me induce the similar probability induced by the original E1. So E2 is not chosen. So he thinks to himself, well, I can actually have a policy which will make the receiver indifferent between the chosen expert and myself. I do so by inducing the exact same distribution on P under the state H bar. So I will also flip a coin and choose delta, and choose a delta coin, and under H bar, P will be recommended. So that will make the decision maker indifferent between the two experts. I will do so by, and while correlating with the state W. I will use the coin in full correlation with the state W. So I will put as mass possible on this outcome when W happens.
But why not
now, wait, Sergio. Wait. If I say wait, I cannot even hear you on the Zoom. So in equilibrium, you should not continue the question. I'll let you answer. Just let me finish the proof. So now E2 says the policymaker is indifferent between both of us, but if he happens to choose me, I'm actually going to be better off than if he chooses E1. So now let him shave a little bit off delta and shave a little bit off his payoff, but still get, increase both utilities. And now the policymaker is no longer indifferent. He chooses him for sure, and E2 is better off. Okay, so that's, oh, I forgot the last. So this is, yeah. So these are the last two bullets, which I mentioned, but forgot to share with you. Okay, so that's the intuition. And essentially, I can finish, I don't want to finish the talk here because I want to give you the two implications under the example, and time permitting, I will move to the general model. So what does it mean that the policymaker gets everything that he could? Well, first of all, it says that maybe he's actually strictly better off listening to a single expert than listening to both experts. We know he's weakly better off. He cannot do better than one, but maybe he's strictly better off. Well, we don't know that for sure, but at least in this example, I will show you in a minute, he's going to be strictly better off than in the alternative game where he can actually listen to both experts. This is from the policymaker's point of view. This is kind of, I think, a surprising outcome. 5 minutes, yeah. From the expert's point of view, I think there's also a surprising outcome. The expert's point of view, they enter the game saying, wow, we have this advantage. Not only do we get access to the information, we have our commitment power, which would allow us to use that information and extract all of the information as surplus. And now they think to themselves, well, if the policymaker gets the full surplus, maybe that commitment power was a double-edged sword. Maybe I should not have had commitment power. Maybe I were better off without my commitment power, which is obviously not the case if there was just a single expert. So let's look at the numbers for both. So now I'm going to take the result of the original game and compare it to two other possible games. In the first, I will ask what happens in the alternative game where both experts, the signals of both agents are realized. And for simplicity, assume that the prior on the state H bar is a half. And now we can consider the following strategy tuple. The agents commit to their own optimal action, namely what they would have done if they were the single agent if they were, if they were just, there's only them out there. And now we have to ask, what does the policymaker do? Because now he now gets two recommendations. So the policymaker in our strategy tuple is going to adopt the policy P only if both recommend it. Okay? And this turns out to be an equilibrium of the game. And you can guess that in the equilibrium of this game, by the way, it's not a unique equilibrium. It's easy to observe that if both agents give the full information to the sender, to the receiver, that would also be an equilibrium. But unfortunately, there exists another equilibrium, and this equilibrium is actually worse than the only equilibrium in the previous setting. So the principle, the decision maker is worse off. Now let's take the agent's perspective and ask whether he's happy. The expert's perspective asks, are they happy with their commitment power? So consider again the same game. The principle, the decision maker chooses one agent, but that agent has no commitment power. Well, it's easy to see that without any commitment power, he cannot really do anything, and he might as well, because alpha is 1/2, he might as well recommend his preferred action. And because alpha is 1/2, the decision maker is happy to take the recommendation because he's going to be indifferent. And therefore, the expert utilities originally were 1/2 plus 1 minus beta 1/2. This is the formula I gave you before. Now, if they do that, both experts actually recommend their preferred action. The policymaker adopts it. And it turns out that at the bottom of the slide, this is the number that they get. I will not go through, I will not try to convince you that these are the numbers, but you can do the very simple math yourself. And this turns out to be better than what they get under commitment power. I will not go through the model, because lack of time, I will just mention again, what is at this point, you can probably do a very simple exercise and just write the paper yourself. I think the example is sufficiently rich to disclose what is the general example model that we work with. But something which I want to emphasize is the assumption under which the result holds. And there are two things which were critical in the analysis. One was the assumption that is on the board in front of you, namely, for every pair of senders, And any sender and any signal of, in any state which is revealed to sender J, namely in his support, there exists an alternative state for agent I, where agent I is completely aligned, a positive probability state, where agent I is completely aligned with the receiver. So it is never the case that one agent, whatever he sees, can rule out the existence of other agents who are completely aligned with the receiver. So no matter what he sees, he cannot rule it out. Now, this assumption, through the referee reports, I can tell you this assumption has received a lot of criticism. So here's our way to justify it. First, it holds in the, if you were happy with this, the e-cigarette example, it just holds there. Second, it holds whenever mu has full support, of course, and there are no redundant actions from each agent, from each of the experts' perspective. And it also holds if it doesn't hold for any mu, then it holds for any perturbation of mu because of the full support assumption. The second thing which I want to emphasize is that in the example, and by the way, in the way that we describe the result in the paper, we assume that each expert can only signal about his payoff relevant states. And as Sergio asked, this is not really necessary. It is enough that the agent cannot fully disclose information about states where he doesn't, payoff irrelevant states. So he can condition on payoff irrelevant states as long as the signal does not fully disclose what they are. So as long as there's some ambiguity. And the way to justify it is to say, well, like in the e-cigarette example, if you care about children, you're probably an expert on children's health. And if you don't care about women, you might know something about it, but you can't really know the real state. You don't have enough information to know the real state, and vice versa.
So that we have time for a question or two.
Related literature, I will leave this on the board and will say thank you without showing a slide. By the way, thank you means also thank you to the organizer for arranging this wonderful, wonderful workshop. Thank you very much.
Thank you. 2 questions maybe, if there are.
I have a question, but since I already asked, I'll let somebody else ask first.
I have a question about the proof, if that's fine. So can you go back to the intuition? So I think I didn't fully understand this simulate E1 signal. This is a mixed strategy equilibrium, right? So I don't know in advance what would be the information structure that expert 1 will propose. Okay, so you are correct. In the intuition that I provide here is for the pure equilibrium outcome. Namely, so we're thinking about the intuition as stated here is for the pure equilibrium outcome, but it turns out that that intuition can also be extended to the mixed equilibrium. And in fact, the result holds for all equilibrium, for all mixed equilibrium. Right, the intuition I give here is true, it's restricted only for the pure equilibrium. By the way, talking about mixed equilibrium, I want to make sure everyone understands what I'm talking about. People, the experts state they're mixed, so a probability distribution over signaling schemes. A vector of signaling scheme is realized, then only the receiver chooses which expert to work with. Because if you reverse the order, then you just get the pure outcome, right? So it's important to understand that what happens here is that the signaling schemes are realized, only then the expert gets to choose, the receiver gets to choose who he works with. So and the result holds under all mixed equilibrium. But it seems that there is some difficult step here, no? A non-trivial step.
I'll take that as a compliment, but the answer
no, or at least like less.
Let me say, I wanted to start with the following. If you plan to teach Bayesian persuasion, I think this paper is sufficiently simple to give it as an exercise to students.
So Ron, I have a follow-up about the intuition, if it's okay. And I have a simpler intuition, and I think it must be incomplete. And the simpler intuition is this Bertrand competition. And sure, they're not competing in prices, but the similarity is basically the expert is going to be selected if it offers a higher expected payoff to the receiver. So of course, if we offer anything less than full disclosure to the receiver, we can undercut. So this could be an equilibrium. So in equilibrium, we must just give full payoff to the receiver. And that's pretty much the proof, except there's one gap, I think, which is it's not automatic in your model that I always prefer to be selected, unlike in classical Bertrand. And I think that's why you need this extra assumption that I cannot signal about the other person. So is this roughly the correct intuition?
Roughly speaking, namely, I wanted to say no just before your last statement, right? It is not the case that they want to be chosen. That is not the case here. By the way, when I did not go over the literature, related literature, but in some of the other models that inherently want to be chosen. There are models out there of competing centers where they want to be chosen. So they bring an investment opportunity and they want to be chosen, or they get paid for being chosen, or whatever. This is not the case here. And this raises the difficulty. So it's not only a simple, so you want to be chosen, and while being chosen, also benefit from that.
Now, what happens if Y and W are not independent? In fact, they are, say, negatively correlated. And the example I have in mind is that Y is really the payoff to, is something that is a private payoff to expert 1, and W is a private payoff to expert 2, or something like that.
Sergio, this is the only assumption I need of the probability distribution. They could be correlated, whatever. It doesn't matter.
Well, I can't parse it yet to understand what it means. But
it means that the probability over the tuple of states has to be such that it is never the case that agent I, or agent J, sorry, can rule out the possibility, maybe it has small probability, but it cannot rule it out, that I is fully aligned with the receiver.
So I think it rules out the example I have in mind. If I understand
correctly. Perfectly negatively correlated, that probably is that it rules out.
Yeah.
Yes.
Yeah, that's what I had. Okay. Okay.
Other than that, they can be correlated in whatever way you want. There's no assumption other than this on the probability distribution.
Yeah, I mean, you need a positive probability to do this undercutting. Yes, essentially, that's.